So we have just given the sketch of the proof of this particular theorem. There's only one part of the sketch which was missing. That's why I'm calling it a sketch. Otherwise, I've given the proof. But that part is actually long and tedious. So that part I want you to do yourself. Now, once we have the theorem, we can now talk about its consequences. And as we will see, the consequences are actually very important. Firstly, so let's, the first consequence is that positive recurrence and null recurrence are both class properties. So this means that if I is positive recurrent and I communicates with J, then J is also positive recurrent. Similarly, if I is null recurrent and I communicates with J, then J is also null recurrent. This is a very important statement, as you can understand. In particular, this means if one state in an irreducible Markov chain is positive recurrent, then all states are positive recurrent. A similar statement holds with null recurrence also. If this happens, that is, if you have an irreducible Markov chain with one and hence all states are positive recurrent, then we call the Markov chain positive recurrent. Similarly, we will call a Markov chain null recurrent when it is irreducible and one and hence all states are null recurrent. I give it as an exercise to you to prove this corollary. I'm not proving it for you. Now this, I give some hints. So there are actually multiple ways of doing it, but I want you to do it using the last theorem that we proved. First, observe that it is enough to establish that positive recurrence is a class property. Why? Because recurrence is already a class property. So if positive recurrence is a class property, then automatically null recurrence also has to become a class property. There is no other way. Check it yourself or convince yourself that this is the case. So we only have to prove that positive recurrence is a class property because, as I said, recurrence is already taken care of. Okay. Then, without loss of generator, we can assume that the Markov chain is irreducible. Why? Because if not, you can restrict each class and work with it. Why does it work? Convince yourself. Okay. Why can we do that? Convince yourself. It has to do with the fact that all the recurrent classes are closed. Okay. But still, convince yourself that it's enough to prove this result when the Markov chain is irreducible. Because if not, we'll just restrict to each of the classes and take care of this. Each of the recurrent classes actually, and take care of it. Okay, fine. Then how do we show this in the irreducible case? In other words, what we have to show here is that if you have an irreducible Markov chain, and one state is positive recurrent, then all states are positive recurrent. This is what you have to show. Now here is what we're going to use the last theorem, in the sense that the theorem we just proved. Well, we gave the sketch of proof today. And there will be part of the previous proof of the previous theorem also that would be important. So one portion of the proof of the previous theorem, which was covered in the last lecture, will also become important. So that's all hint I'm going to give you. That's all hints I'm going to give you. You have to now solve it. Okay, so another consequence is that an irreducible positive recurrent Markov chain has a unique stationary distribution given by phi I equal to 1 over expected return time to I. Now let's first prove this, okay? And then we'll talk about how important this is. Now from the theorem, we know that the stationary distribution exists and is unique. This is something we have already proved. Now fix the state I. Now this is a positive recurrent Markov chain, so therefore this state I is positive recurrent. So then this is of course, this is it's in particular, it's a recurrent, and therefore this is an invariant measure. Okay? Not only that this is an invariant measure, since I is positive recurrent because of the assumptions, the normalized version of nu, which is pi, is actually a stationary distribution. This is the unique stationary distribution because the stationary distribution has already been proved to be unique. Okay. Now note that nu j has this form. So therefore, in particular, for j equal to I, we get, sorry, not nu j, pi j has this form. Therefore, for j equal to I, we get pi I is nu I over expected return time to I. But nu I is 1. We already know that. So therefore, pi I is 1 over expected return time to I. Now note that we just fixed the state I, but this I is arbitrary. We could have fixed some other state I also. All the states are positive recurrent because positive recurrence is a class property and the Markov chain is irreducible. So therefore, all states are positive recurrent. We could have just done it with any state I, and that would show that pi I would be equal to 1 over this for any state I. And of course, the point is that the stationary distribution is unique. So therefore, since I is arbitrary, this corollary follows. We can start with any state I, and we can conclude that for that particular state pi I has to be of this form. And pi is unique, so therefore pi I always has to be of this form, all state I. Okay, so this therefore tells us that for an irreducible positive recurrent Markov chain, this unique stationary distribution is given by pi I is 1 over expected return time to I. Now, intuitively, this means on the average, the Markov chain visits the state I exactly once in this amount of time, expected return time amount of time. Okay, so on the average, it will visit once is this amount of time. So therefore, the long run proportion of visiting I should be 1 over this. Because in this amount of time, the number of visits is 1. So therefore, unit amount of time, the number of visits should be, okay, this is all heuristics, okay, 1 over this guy. And that should be it is on the average. So therefore, that should be the long run proportion, long-term proportion of visiting I. And that, the long run proportion of each state should actually be the stationary distribution. Why? Because if you have already reached the long run proportion, what is the stationary distribution anyway? A stationary distribution is a distribution, a probability distribution, such that if you start the Markov chain with that probability distribution and take one step, then after one step also, the probability distribution will remain the same. So in other words, if x0 follows pi, then x1 also has to follow pi. That's the definition of stationary distribution. If pi happens to be, so if pi I happens to be the proportion, long run proportion of I, so if you start that Markov chain in the long run proportion of I, then one step should not change the long run proportion, and therefore the distribution of x1 should remain the same. And that tells you that heuristically why one should expect that the long run proportion of I should give you the stationary distribution. Okay, so therefore, this intuitively is obvious that this is the right stationary distribution. Now, this is also useful computationally. This will be extremely useful to find the expected return time to I as 1 over pi I. Because pi I can always be computed from these equations. Okay? Pi transpose p equal to pi transpose and summation of pi j is equal to 1. This is a probability distribution. Of course, this may not always be easy to make this computation, but when, say, we have a 3-state Markov chain or a 4-state Markov chain and so on, in those cases, definitely this can be computed. And then once this can be computed, you can use that to compute the expected return time to I using this formula here. So this is a very nice computational recipe for finding expected return times. Of course, this computation may not be easy, as I said. For that, we have to use something called reversibility. That will help us in the computation.